Okay, so today we're gonna introduce what's the application of the helical coil torsion springs. Okay, and the helical coil springs can be loaded with torsional end load. A spatial ends are used to allow a force to be applied at distance from the coil axis, and usually used over a rod to maintain alignment and provide buckling resistance. Okay, so it's uh, a video of the this torsional spring. Okay, the torsional spring. Okay, so I'm gonna tell you the result first, and then we'll just tell you the result first, and then I will teach how those value and how those equation comes from. Okay, so this is the torsional spring, right? So of course, first we have to figure out what is the spring constant is. Okay, and this torsion springs can be applied to at the end of its length with a specific angle. Okay, so we apply the force here. Okay, and the first parameter that we have to figure out is the spring constant. Okay, spring constant. Of course, the other parameters that have to be considered, well, is the same as before. Okay, the compressive or the extension spring. Okay. Okay, so while it's a very basic physics, so when we apply the force, and this force is perpendicular to the length, and the force we equals to torque divided by length, and torque equals to force times the length. Okay, and if this force apply to the length with a specific angle, and the force will equal to torque divided by length times sine theta. Okay, sine theta in this case is 60 degree. Of course, the torque equals to force times length times the sine theta. Okay. Okay, so how to evaluate the spring rate or spring constant, right? We can figure it out as what we already learned previously. We can figure it out from, what's the load they apply and what's the deflection, right? To figure out what is the spring rate is. And also, we can evaluate by its dimension and the material's properties, right? Okay, so the spring rate equals to torque divided by angle. This angle is what the angle that we apply. Okay, and this angle is 45. In this case, it's 270 degree. Okay, so in this case, the rate, spring rate equals to 350 divided by 270. Okay, okay. For example, it's a 5 Newton, right? Times the length, okay, divided by the angle. Therefore, the spring rate equals to 1.296, okay, 1.3. Okay, so let's suppose the few load position. Okay, there are a few load positions. First is at the very beginning, the initial position and position 1, 2, and 3. Okay, so for the position 1, we apply the force, right? We apply the force that the one side of the lens is rotated 45 degree. In the second case, the second position, the lens is rotated 180 degree. In the third position, this lens is rotated 270 degree. Okay, if the constant, the rate constant, or say the spring rate remain the same. Okay, we say it's 1.3, around 1.3, and for this position 1, whose torque is 55.3 Newton meter, and the torque applied at the position 2 equals 233.33 Newton meter. Okay, the third position with the torque that is about the 350 Newton meter. Okay, and the force, of course, the higher torque with the higher force applied. Okay. Okay. So the key factor, that's what I mentioned previously, spring rate, the torque at the length one, okay, at the length one or the length two, okay, and the spring stress and the diameter over diameter and the overall length, okay, and the overall length. Okay, so as what I mentioned previously, the spring rate can be also evaluated by the dimension and the material property, right? So the spring rate can be evaluated by the Young's modulus and the diameter, okay? The wire diameter and the mean coil diameter and the number of active coil, okay? So in this case, we can evaluate the spring rate of spring constant by the materials property and the dimension, okay? And the dimension. Okay? It's similar to what we already learned, right? From the compressor and the extension spring. Okay. And the spring stress with the round wire. In this round wire, right? It's cross sections round. Okay, it's a round shape. Okay, so the spring stress equal to 32 m is the moment divided by pi d cube times the kb. Kb is the correlation vector. Okay, it's the same as what we already learned previously. Okay, so here this is the stress correlation vector, and C is the spring index. Okay, it's the spring index. Okay, so we roughly know what's the result is, what those results are, and how to get those results. Okay, so let's see. For this spring, sorry, for this torsion spring, okay, torsion spring, it is subjected to the bending, right? Subject to bending, and we need a correlation vector in front of it. So this is the MC over I, represents the bending stress, times the correlation vector. And the stress correlation vector at inner and outer fibers has been found analytically for round wire. That means there are two different stresses, right? At the inner and outer fibers. Okay. Therefore, for the Ki, I means inner, is Ki, if it is inner, equals to 2CQ minus C minus 1 over 2C times C minus 1. Okay, and this KO represents the outer fiber. Okay, the correlation vector of the outer fiber equals to this term. And the Ki is always larger. Okay, it's always larger. Now you can imagine that, right? Because the curvature and the force applied, therefore the Ki, that's mean the stress, okay? The stress sigma at the inner ring is always higher. Okay, so the Ki is always higher given the highest stress at the inner fiber. Okay, and with the bending moment N equals to Fr for round wire, the bending stress equals to, right? So this is what we get previously, right? So what we get previously here, right? Here. It's the same, right? Okay. Okay, so there are some parameters that we can calculate it. First is the spring rate and the bending stress, correlation vector, and the spring index. Okay, for calculation for the key design, vector is the length, two lenses, and the diameter and the length. Okay, for the design of the torsion spring. Okay. Okay, so what is a free lens? The free state, sorry, the free state, the free state. Or say the free lens, right? Free lens equals to D, the wire diameter times the number of the active coil plus one. Okay, so in this distance presents the L, or say L naught. Okay. Okay. Anyway, as you know, right, what it is. Okay, and D is the wire diameter. Okay, so I just make something wrong. They should be the capital D. Sorry, let's just remove it. It's not correct. Okay, it should be the capital D. Okay. Okay. So the lens extension under load. So what's the, if we just apply the force, right? Apply the force for this torsion spring. Okay, so this torsion spring we rotate it, right? So when we apply the force at each length, right? So it will rotate it. Okay. And this length under load equals to the wire diameter times the NA plus 1 plus theta. And the theta is the number of the additional rotation. Okay. The force applied to the lens, and it will rotate it, right? We'll rotate it. Okay, so this figure tells us when the spring, the torsion spring under a load, what we get. We will get length become longer, right? So in this case, if we apply the force to rotate the lens with the angle of 720, and this free lens, this lens will increase. Say the length of extension will increase, right? Compared to the free lens, right? It's the increase. Okay. So when we rotate a specific angle, this lens will increase. Okay, when we apply the higher load, that means the rotate angle increase. Okay, so this free lens, or say this lens will increase. The load length increase compared to the free lens. Okay, so when we rotate 180 and when we rotate a whole circle 360, so you will have the lens with the one more coil. Okay, with the 360 degree. Okay. Okay, so when this one lens rotate, one bar rotated 720 degree, that's mean 2 times the 360, right? We'll have the additional 2 rotation. Okay, 2 rotation, 1 and 2. Okay. And meanwhile, this coil diameter, or say the mean coil diameter, will reduced. Okay, when we apply the force to make the low bars rotated with 270 degree. That means this length, load length will increase 2 terms, 2 rotations, right? And the mean coil diameter will reduced. Okay, its mean coil diameter will reduced. Okay. So this mean coil diameter under load equals to D1. Here the D1 represents the mean coil diameter at free length. As MB is the number of the body coil, okay, and theta is the loading rotation. It's a loading rotation. Okay. So the coil diameter change under load, external coil diameter equals to DO. The O represents the outer or the outer diameter. Okay, outer diameter equal D1, the free length without any force apply, times the number of body coil divided by the number of body coil plus the theta plus the D wire diameter. Okay, and the inner coil diameter equals to the D1 times the MB divided by MB plus theta minus, okay, minus D, the coil diameter. Okay. Okay, so let's look in the other situation is if this free length bar is rotated the other direction. Previously, we say the this bar is rotated at counterclockwise. And in this case, if it's rotated clockwise, what's the situation should be? The situation is that the free length, okay, will become shorter, okay, become shorter, and the mean coil diameter will increase, okay, and the mean coil diameter will increase, okay, the mean coil diameter, okay, will increase, okay, 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 so the mean coil diameter will increase. Okay, so if this torsion spring is applied to bar, that means this rod is it's at the center of this torsion spring, and the diameter of the rod is smaller than the inner diameter of the torsion spring. Okay, and we already know what's the definition, what's the calculation of the inner diameter, right? And the rod diameter has to be smaller than that. Okay, that should be smaller than that if your application is in this case. Okay, so the other one is if this ring or tube is outside the torsion spring. That's mean the tube diameter, or we'll say the tube inner diameter. Okay, the tube diameter just here. Okay, the tube inner diameter has to be larger than the DO, this is the outer diameter of the torsion spring. Okay, of the torsion spring. Okay, so what's the terms? The coil terms contribution to length. Okay, so the NA represents the number of the active coil. Okay, so with this yellow, the red color represents the terms that we have to count it. So the NA, the number of active coil, right, represents in red color. And in this case, MB terms the number of the body terms, okay, which is not counting the lengths, okay, the two lengths, okay, and the two lengths coil or terms is calculated or is taken into account by the NE, which is the end term, okay, the end term, Okay, the N term. Okay, and we define the coil terms, okay, of the end at the two ends or two lengths. Okay, defined as NE equals to L1 plus L2 divided by 3 pi d. I will explain how this number get from. Okay, but you have to just remember this first. Okay, so this represents, okay, N term. Okay, N term. And number of the active coil equals to MB, the body number of body coil and the number of the N terms, right? So it's the whole terms, okay, has to be taken into account. Okay, and the coil diameter tolerance. So tolerance is defined as the the dimension that is acceptable for some differences. Okay, so the DTOL represents the tolerance. That's mean, okay, so let's say for this torsion spring, we can define this inner diameter is about 10 millimeter. However, we can accept its tolerance is about 9.9 diameter. Okay, 9.9 diameter. Okay. So the tolerance of the coil diameter is equal to 1,000 plus C1. C here is the spring index plus 20 times the D plus 2 divided by 10,000. Okay. Okay, so there's the table represents the end position tolerance, the tolerance for the helical coil torsion spring for D over D ratio up to including 16. Okay, so when this terms, the total coil over 30 turns and the tolerance equals to plus minus 25 degree. Okay, 25 degree. Okay, if this term, I said 3 turns, and its tolerance is a degree. Okay, it's a degree. Okay, so this the table or design handbook shows how is this conventional tolerance for torsion spring. Okay, for torsion spring. Okay, so there are different type of the torsion spring here. It depends on what your application is. Okay, so let's look into what's the terminology. Okay, so now we define the initial unloaded partial terms in coil body. That's mean this torsion spring without load apply. And we define the partial term in the coil body, NP equals to beta divided by 360. Okay, so in this case, this NP represents the partial terms here. Okay, so this NP will equals to the beta here, the initial unloaded terms, the beta divided by 360. Okay. And the number of body terms NB will be full terms plus the initial partial term NP. Therefore, the NB is the number of the body terms equal to the integer plus NP, right? Plus NP. Okay, plus NP. Okay, so spring rate for torsion spring. Okay. Previous I already tell you guys the results of the spring rate, right? And how to calculate it. Okay, what the equation is. So now I'm gonna tell you why we got that spring rate or spring constant. Okay, so for the angular deflection, It's commonly expressed in both radius and the terms revolution. Okay, so you will see the units is with the radius or the revolutions. Okay, if a terms contain revolutions, the variable will be expressed with a point sign. And the spring rate, if it's linear, so we say that the prime side represents the revolution terms, revolution of the spring constant. Okay, so as you see, the prime size represents the terms contain the revolution. Okay, so for the K prime, the spring rate, spring constant equal to M1 divided by theta prime 1. Okay, theta prime 1. And the M here can be expressed as the moment as the FL or FR. Okay, the load applied times the length, okay? Okay? Okay, so now the deflection in the body of the torsion spring. Deflection. So when we talk about the deflection, what do you think of? What's the method? What's the theory that you think of? Yeah, the Cartesian theory, right? We can use the Cartesian theory to find the deflection in radius, okay, in body of a torsion spring. So because this torsion spring is subjecting to bending stress, and what is the bending stress? What is the let's say the energy, Castellian energy for bending stress here, right? The U equals to m squared dx over 2EI, right? And the m here is the moment equals to FL or FR. And the integer over the length of the body coil while the force F will deflect through a distance r theta, right? Okay. So if the deflection, it can be defines the r theta, equals to the energy, take the derivative with respect to, in this case, it's force, F, right? It's force, okay? From 0 to pi d times mb. Okay, so we can take the derivative of this equation with respect to F, and we get this term, and we just integration. Okay, so finally, we get the theta. Okay, we can use I for run while the circle cross section, right? And solving for theta, right? Solving for theta here. So we got the result is this, and we replace the FR with the moment. Therefore, say the K, the theta equals to this term. Okay, any problem on that? Okay. So the deflection in the end of the spring must be count 4, right? So the angle subtended by the end deflection is obtained from the standard cantilever beam. Okay, so what's this mean? Okay, let's go back to the figure of the okay, let's say this. Oh, let me see. Okay. So if we only account for the length here, okay? So this length can be regarded as the single or and simple cantilever beam when the force applied to it. Okay, so in this case, it's just just a cantilever beam with the point load applied. Okay. Okay. Okay, so let's go back to what we get, right? So the angle, okay, subtended by the end deflection is obtained from the standard cantilever beam, okay? Therefore, the theta E means end, the end theta equals to y deflection over the L, the length, right? So we can check the table or any handbook. Okay. So the theta E will equal to FL squared divided by 3EI. Okay, 3EI. And because it's a wrong cross section, right? So the I equals to pi d power 4 divided by 64. Okay, and then we get the theta E equals to this term. Okay, so what we got already, we got the theta for this coil, right? Or say the deflection of the coil body, of the body coil here. And we got the deflection of these two end. Okay, two end. Okay. So the total angular deflection is obtained by combining the body, right, and end deflection, body and end deflections. With the end lengths of the L1 and L2 combining two deflections previously obtained, it gives the theta theta t represents the total, right? So this is the body coil deflection, and this is the one length, the one end length deflection, and this is the other end length deflection. Okay, so we just summation of the three terms, and we get this. Okay, so we just extract this term out. Okay. Okay, and then we can define the number of active terms. Okay, the number of active terms. And this term represents the number of active terms, an A here, right? And then we define the second term as the number of n terms, right? Number of n terms. Okay, so that's why previously in the very beginning, I just ask you guys to remember it first, right? I will explain those values later. Let me see. Sorry. I should have the number of the n term, but I forgot where is it. Huh. Okay. Anyway, I forgot where is it. Okay, so we got a total deflection, and this term is the effect of the ends. Okay. Okay, so the spring rate in torsion spring K will equals to M over the theta T. T represents the total, right? M over theta T equals to this term. Okay, so how to find this? We just plug the theta T in here. What is the theta T? This is the theta T, right? So we just plug this, right? In here. Okay, so we find the spring rate. Okay, so we can convert it K to K prime. If you still remember, prom means revolution, means terms. Okay, so the K prom just equals to this term. So this values for torque per radius, and this term is used for the torque per term. Okay, per term. Okay, so they compensate for the effect of friction. That's our friction between each coil. Okay, between coil and the Amber test shows that 10.2 should be increased to 10.8. So theoretically, we figure out the number should be 10.2, but experimentally, we should increase this number to 10.8. Okay, therefore we get this K prime, spring constant in torque per term equals to this term. Okay. And from the previous equation, 27, this one, sorry, I erased them all. For this one, theta t equals to this term, right? And we can modify, right? Modify this equation, okay? To theta t prime equals to the 10.8 md over lowercase d power 4 times the Young's modulus, okay? Times this term. Okay, so decrease of side diameter, inside diameter, torsion spring under load will experience a change in coil diameter. If a spring is over a pin, the inside diameter of the coil must be allowed to decrease to the pin diameter. And angular deflection of the body of the coil, extracted from the total deflection, is the theta C prime. Okay, the theta C prime. So the equation 52, this equation okay, extract this term out. Okay, and we got to see that D prime equals to this term. And the new helix diameter D prime of a deflection coil is MBD. This is the mean coil diameter divided by MB, the number of body coil diameter, plus C theta prime C. Okay. Okay, so this theta prime represents the angular deflection of the body coil, right? Okay, in radius. Okay, in radius. Okay, in radius. Okay, and the new helix diameter D prime, okay, equals to MB times the D, okay, over the MB plus theta prime. And the new inside diameter DI prime equals to D prime here, minus the wire diameter, okay, minus the wire diameter. Okay, so for the dimensional clearance data between the body coil number and the pin of this pin diameter, okay? So that's what I mentioned previously. If we put this if this torsion spring is applied for a rod inside, okay? So there's a clearance between these two diameters. Okay, and this clearance equals to D prime. What is a D prime? D prime is here. The new helix diameter. Okay, the D prime minus the wire diameter minus the DP. DP is the pin diameter, right? The pin diameter. Okay, and we can plug those equations. D prime here, right here, minus D minus DP. Okay, and we can solve the MB, which is the number of the body coil, equals to this term. And this gives the number of the body terms necessary to ensure a specific diametral clearance. Okay, so from the design point of view, we have to know what's the name of code, the name of the body terms. Okay, are necessary to ensure the specific the metro clearance. Okay, so you want the clearance or the gap or the spacer between the rod and the inner diameter of the torsional spring. Okay. So this static transfer torsion spring to obtain the normal unit transfer spring while loaded in bending. Okay. The volume values given for torsion spring this table, okay, by 0.55, 0.577, which can be obtained depends from the based on the torsional energy method. Okay. Okay. So it also depends on the Y, the spring Y, before or after set removal process. Okay, so if you still remember this table, okay. Okay, therefore for the yielding stress, it's tension yielding stress. Okay, for the music wire cultural carbon steel, it's 0.78 SUT, right? How to get SUT? I have to figure out what's the A and M, right? Parameters. Okay, so there are different materials for the different yielding stress. Okay, different yielding stress. Okay, so for thick stress for torsional spring, the science method and the Zimmermann data were only for torsional stresses, so are not applicable looking better data for induced limits in bending. So we can use the table here, 10-10 from the associated spring for torsion springs with the repeated loading, okay, to obtain the recommended maximum bending stress. It's the repeating stress. Okay, it's a repeating stress. Okay. So this table represents the maximum recommended bending stress. Okay, for the helical torsion springs in cyclic loading as percent of the SUT. Okay, as the percent of SUT. Okay. So this means the 53% of the SUT. Okay, is it 40% and 62% and 60% and so on. Okay. So it is 55% SUT, right, equals to the SR. SR is the recommended maximum bending stress. Okay, so now next we can apply the Gerber's criteria to obtain the endurance limits. Okay, and this repeating loading is assumed. What is repeating loading here, right? We can find it from this table, right? We can find it from this table, okay? And we can plug in here, here, and here. We get its endurance limits. And this counts for corrections for size, surface finish, and type of loading, but not for temperature or the Mesmer effects, okay? Okay, so this is the what we already learned, right? And last semester, this is the different criteria, failure criteria, right? So for the sprints, we usually use the Gerber criteria here. Okay, for this line. Okay, for this line. Okay. Okay, so we can find the SA, the alternating stresses. Okay, alternating stresses. Okay, so depends on the different criteria with its load line. Okay, with its load line. Okay, so in this case, this is the Gerber's criteria for the torsion spring. Okay. Okay. And you can define safety vector equals to the SA divided by sigma A. Okay, so let me see, maybe I notation something wrong here. Oh, I notation something wrong here, but well, it's not big issue. So this should be S and S. Okay, so we'll load this load line from the from this Gerber's figures here. So we have this load line. Okay, SA over SM. Okay. Yes, SA over SM R. Okay. So we can find the it's the safety vector. So if our situation is right here and we can find a ratio between this distance compared to this distance, right? And we can evaluate its safety vector. Okay, its safety vector. Okay, so we got its safety vector. So this point is the SA. Okay, this point. Okay, this point is SA here. Okay, and then we plug those terms here. Okay, and we'll find safety vector here. Okay. Okay, this is the table what I use, right? So we can check the amplitude, the SA, and the static coordination of the strands that input and intercept in the first quadrant of the Gerber, okay, and the longer failure criteria, okay. Wow, it's what we already learned, right? How to those figures like this, okay, like this. Okay, and next there are some examples. I think you guys can finish. You can just take a look at this exercise and hope you can finish by yourself, okay? And as a practice. And today's class is end here. Thank you.